Let's take a look at an example of a flux integral. So we've got this vector field, and we care about how this vector field is flowing through the following surface. The surface in question is going to be the graph of z equals cosine x plus sine of 2y above the region R. So I have to, I want to limit my region. I don't want to say over this entire surface because the surface go on forever. So I'm going to restrict my surface to be the surface given by this function above the region R, which is going to be a triangle with vertices at 0, 0, 5, 0, and 0, 5. So we care about we have vertices at 0, 0, 5, 0, oops, that's 0, 5, and 5, 0. So above this region R, I don't want to shade it in. Above this region R, we're going to look at the surface. So whatever the surface is doing from the top down, we only care what's going on above this triangle. And then we're going to calculate this vector field flowing through the funky surface above this triangle. Any questions? So here's 0, 0, 5, 0, and 0, 5. All right, so I just drew a region, and you know this is going to lead to a double integral. Here's our double integral dx dy. So you know we're going to be using our old skill of describing this region. What's y between, what's x between. Let's see how these calculations work. So I need to evaluate the function, I need to evaluate the vector field at x, y, and f at x, y. So what we're doing is we're replacing z with our function. So this z is our f at x, y, the surface. So I need to evaluate, let's see, let's just break it off into pieces. F at x, y, and z, which is f at x, y. This is going to equal, it's y times z, so I need y times this function. That's all this color. The next term is plus xy times j plus another xy times k. I don't like this was repeated, but I'm happy that it doesn't involve z. So I just had to replace the z with our function. So this is just this first piece, the function evaluated at the surface. Now I need the dot dA part, the part that we didn't really talk about. So I need to compute dA. So our function f at xy is cosine x plus sine of 2y. So our function f at xy is cosine x plus sine of 2y. And I need our two partial derivatives for dA. So I need fx. So the derivative with respect to x is going to be derivative of cosine, which is negative sine. The derivative of sine of 2y with respect to x is 0. And I need fy. The derivative of sine of 2y is cosine of 2y times 2. And the derivative of cosine x with respect to y is 0. So here's fx and fy. If we imagine z equals our function and we subtract and we rewrite it as f at x, z minus f at xy, that's why the fx and the fy show up negative. That still doesn't answer the question, where does this come from? I'm just saying that's why these negatives appear from a mechanical standpoint. So our dA the dA is going to be minus fxi minus sine x I minus fyj, so minus fy minus 2 cosine of 2y, spelled cosine wrong, times j plus 1 times k. 1 times k is looking at this as z equals f at xy and taking the derivative of z with respect to z and coming up with 1. So the reason that we have this 1k, it's because we're writing this as a function. It's the 1. This is the 1 that shows up as the k. So here is our we took derivatives to get something for dA, just like we did in a line integral, where we took derivatives to get the dr. Now we write the dot product of the integral f, dot product of f evaluated at the function, at the surface, dot dA. And we also run out of space. I started writing this problem and I'm like, oh, there's no way it'll fit on this bottom half of the piece of paper. And yet here we are. I did it anyway. So now I need to set up a double integral. I need the vector field evaluated at the surface, which is this expression. So I need y times cosine x plus sine of 2y This is all going to need to be crammed up together because this is a very long. I'm not going to fit it on one line. So it's going to be y times cosine x plus sine of 2y all times I plus xy times j plus xy times k dot dA. So this is the dot product with the sine x minus 2 cosine y times j 2y. Plus 1k. And then I can describe this as a dx dy or a dy dx. But this is the dA part. dx dy. I shouldn't just start dropping dots when we're actually doing a dot product. Then all we have to do is describe the region. I described it I wrote it dx dy here, so I will have to describe it xy, so x equals and y equals. So now we got to go back and describe the surface, figure out what values we're plugging into the surface. So the last one, we have to go back to our old skill sets, and I did y last. So y goes from 0 to 5. So that's nice and straightforward. Y goes from 0 to 5. Now for a typical y, I have to see what x's we are in between. So the x starts off at 0 and stops when it gets to this line here. So I'm going to fill in the 0. And this goes up to, this line is 5 minus x. We have a slope of -1 and it starts off at 5. So y is 5 minus x, but I need x equals. So that means x is equal to 5 minus y. Solve it for x, 5. So we'll integrate from 0 to 5 minus y. So we change the signs because our dA should be a minus fxi minus fyj plus 1k. So what we want to do is we really want to take the graph z equals f at x, y, and turn it into an equation. This is the hand wavy version of how why the negatives. And so if we rewrite this as an equation, z minus f at x, y equals 0 or equals some constant. Those are the surfaces that we're dealing with. So we want to put the fxy on the same side as the z. So imagine the surface. Imagine the surface minus f at x, y plus z equals some constant. So imagine those surfaces. So even though z equals cosine x plus sine y, we're reading it as the surface minus cosine x minus sine of 2y plus z equals some constant. So that's why those negatives in front of fx and fy. So all this part is in green is the dA. And so that's the three parts that the vector we have here. All this part in green is just there to be the dA. Any other questions? Parentheses, didn't close those. All right. So this is a dot product. So I multiply the i's. So I multiply the i's. So I've got, let's see, we're gonna have, I'm gonna pull this out because this is all y cosine x plus y sine 2y. So I need to multiply this by the sine over here. So I end up with y cosine x sine x integral plus sine of y sine 2y times sine x. That's the product of the I components. Then I need the product of the j components. So it's going to be xy times minus 2 cosine of 2y. That's the product of the j components. Then I need the product of the k components, which is just going to be plus xy. This is still all a double integral. X goes from 0 to 5 minus y, and y goes from 0 to 5. And I set it up as a dx dy integral. Any questions on putting stuff together? Because that was our goal, at least in this problem, just to put stuff together and see how similar this process was to evaluating line integrals. Here's a picture of the surface over which we are integrating. Now, this would be a picture of the entire surface over which we are integrating. And we're only concerned with one piece of it. So let me take a picture. This doesn't show up on the video. Dang. So all I did, what I'm showing is for those of you checking out the video and not seeing the text or the chat come through, I'm just looking at, I went to Wolfram Alpha to look at this surface. So I'm just looking at this surface in Wolfram Alpha, z equals cosine x plus sine of 2y. That was the link that I just sent everybody. So I don't want you to feel left out. I realize that the chat doesn't go along with the video. So if we could see the cosine x plus sine of 2y, as we expect, is just a bunch of peaks and valleys. We got, and everything's all nice and orderly with the cosine x and the sine of 2y. What we're looking at is, if we look at what we're looking at is essentially a piece of one of those hills. So we're looking at this triangle, and above this triangle, it looks like we're going to have a couple of hills and then a couple of valleys. So that's the surface. We're just looking down from the top at all these peaks and valleys, and we're cutting out a triangle. So what it looks like is we have all these peaks and valleys. This is the contour plot. And we have all these different peaks and valleys. So peaks along here, and then it drops into valleys over here. So this is the surface with all of its rolling hills. And we are just looking at one triangle. So we're looking at all the surface where those peaks and valleys above this one triangle. And we're calculating how the vector field, we're calculating how this vector field flows through that surface. The one interpretation that we've used so far for flux integrals is that we can imagine the vector field is the measuring how water is flowing. So the vector field is water flowing through space. And then we put these hills above this triangle. That's like a net, and we could measure the volume of the water flowing through that surface. Any questions? No questions is incorrect. You should have many questions at this point. But in typical fashion, I'm going to let those questions just kind of hang in the air. Let's pause the video here and talk about next steps.